1, 2.
Hello, is that better? Excellent. So, good morning, everyone, and warm welcome
Sound 1, 2.
to this HPC applications track. So, my name is Lyudmila Moskaleva. I'm from the University of the Free State. I'll be chairing this session. Let me first tell you about the format. So we are going to have 4 talks, 4 20-minute talks in this session, followed by a question and answer session, which means that questions are asked after all 4 talks are finished. So please save your questions for later. You will have sufficient time to think about your questions and write them down so that you don't forget. I encourage all speakers to strictly stick to the schedule, since we are already half an hour late. When you have 5 minutes remaining, I will raise my hand like that. When you don't have time anymore, then I will just stand up. Okay, so let me welcome the first speaker of this session, who is Professor Babatunde Abiodun. And Professor Abiodun is from the University of Cape Town. He will give a presentation entitled Simulating Potential Impact of Solar Radiation Modification on African Climate. Welcome, Prof. The stage is yours.
Thank you. While waiting for my something to load up. Okay. Thank you, everyone. It's a pleasure to be here. I want to thank the organizer, HPC, for organizing this, for inviting me to give this talk. I really appreciate it. As she said, this is the topic of my presentation, potential impact of solar radiation modification on African climate. I want to acknowledge the co-authors of this study, and also want to acknowledge the funders. These are the list of people that funded the research. So, we know that climate change is one of the most pressing issues globally. And when we talk about climate change, we know that why climate variability and change can be natural, but scientific investigations have shown that human activities have actually accelerated this climate change in the last decade. And when we talk about climate change, global warming is a signature of climate change. And with this, we see an increase in global temperature over the past decade. Sorry. Oh. Okay, sorry. I'm not used to this. Okay, no problem. So, when we talk about global warming, we see increase in temperature, in global mean temperature, due to emission of greenhouse gases. And all the models all the GCM models agree that this increase is as a result of anthropogenic activities. And they also agree, they also agree that the warming will continue into the future. The value varies from one model to the other, but they say the same thing. Another thing they agree on is that Africa is a hotspot of global warming, of the warming. And the warming results into different things, or it triggers different things, melting of ice, and sea level rise, and so on. And it also altered weather patterns with time. And thinking about the impact of climate change in Africa, these are the pictures that come to mind, ranging from drought to water insecurity, heat stress, flood, food insecurity. And because of these, there have been a lot of debate on how do we address this problem of climate change. Unfortunately, while the negotiation to reduce the emission is very slow, the emission itself continues. Here, I will start with this diagram. It's called Shepard-Napping's diagram. This just to give us like a theoretical illustration of how do we plan to deal with this problem. On the x-axis, we have time. On the y-axis, we have the global mean temperature. This line represents the target that we don't want to cross based on IPCC agreement. That's 1.5 target that we may all know about. We have this curve. If we do, that's what we call the business as usual curve. If we do nothing about addressing this issue, then that will be the path, which means we are somewhere here, very soon we cross that threshold. But if we do all the all the mitigation strategy, ranging that contain the emission of CO2, all those various activities, then we find ourselves in the green curve. What does that still mean? We may still cross that threshold. And we advise not to cross that threshold because it can lead to tipping point. It can cause a lot of catastrophe that the system may not be able to recover from. So the high is on this threshold. How do we not cross it? And if we say, okay, carbon dioxide removal, we start implementing technology that can remove the CO2 in the atmosphere. Remember, this one, mitigation does not remove CO2 in the atmosphere. It only wants to slow down the warming rate. But if we now start to put technology in place to remove the CO2 in the atmosphere, that is carbon dioxide removal strategy. That addresses the problem. Because CO2 is the problem, it addresses it, but the problem is this. It is too slow for us not to cross the threshold. That is where solar radiation modification comes in. Solar radiation modification has been proposed as a means to reflect back some solar radiation from reaching the surface of the earth, thereby we cool the planet. That is the idea of the solar radiation modification. Because when it's deployed, it has the capability to quickly mitigate or limit the warming. Now, before we go on, I just want to stress this. Solar radiation modification is not seen as alternative to these two strategies, mitigation and carbon dioxide removal. It shouldn't be. Why? Because it does not address the problem. Rather, it just tries to be used as something to help us buy time before, so that we will not cross that threshold. As good as it is also, it has risk associated with it. Why? Because it's only targeting temperature. And climate has various variables that we depend on. So it may have good impact on temperature. How about precipitation? How about other variables? So there are a lot of risk associated with it. However, how can we do it? Anything that can reflect radiation back into the atmosphere can be used as solar radiation modification, ranging from putting mirrors into this space, stratospheric injection, and so on. This is the most viable strategy for now. Then we also have marine cloud brightness, which I will be talking about. Sorry, how many minutes do I have? 10. Okay, good. I will need to move fast, sorry. Now, the idea of solar radiation modification was taken or was gotten from nature. Whenever we have eruption, volcanic eruption, it will inject some aerosols into the atmosphere. And this aerosol will block part of the sun, reflect it back, and cool the planet. This is an example from the Mount Pinatubo eruption. And we could see the cooling that followed thereafter. So the scientists said, well, can we use this to address the issue? Do we have the technology to do it? And the answer is yes. They have shown that it is possible for us to implement this, to artificially inject aerosol into the atmosphere. But maybe that's not the question we should be asking. Maybe the question we should be asking is that, should we do it? And when should we do it? So this has generated a lot of controversy, and it has raised a lot of questions among physical scientists, social scientists, politicians, and physical scientists are saying, what will be the impact of this aerosol on the dynamic climate, ocean, and so on? How will it affect? How will it affect various socioeconomic activities that depend on climate variables? So these are the questions that physical scientists are thinking about. Then, in the politics world, people are also saying, who decides whether we should do it or not? And if we are going to do it, when? And where should the action be taking place? Should it take place? And if it goes wrong, who will take the responsibility? So that's why there have been a lot of research activities in this area. And developed countries have been investing a lot on this research, on this kind of solar radiation modification. I know many people in the room may be hearing it for the first time because it's a new thing here. We've not been hearing about it. But in the developed country, they have invested a lot. Just to show you some numbers, shall we go into? And there are also activities to do the field test. Now, there are 3 ways to test if this thing works. Number 1, we could do laboratory test, where we do it in our lab. But the problem with that is that, how realistic is it to the real world? Number 2, we can do field test, where we just go open air fit and do it over in a very small place, over a short time. But the problem with that is that, how realistic is that? Because if you do it, you can't do it for over a long time, because if you do it over a long time, that is deployment. You have started deploying it. It has to be over a short time. But how representative is that to climate? So the one way people have been, so this is one of the experiments that was planned, but unfortunately, they couldn't carry it out because people were saying, no, it's not possible. We don't want that. A lot of criticism. Then, this is already going on. That is marine bright cloudness in Australia. Then the third way is to use models. And that's where their work comes in. That we simulate, we'll be using models to simulate climate. Then we can then use the same tool to study the impact of solar radiation modification on the planet. So this is one of the community experiments. We call it GeoMap, where we look at different scenarios of what solar radiation modification can do to different activities. Then we also have another one. This is another scenario we call another experiment. This is another experiment. We call it glint and arise. Basically, what we did in this experiment is to inject aerosol into the stratosphere at those locations and then see how does it affect the global mean temperature. This is what the was supposed to, under RCP 8.5, this is the situation. But when we injected the aerosol, then this is the warming. For both the two experiments, one used SSP 4.5, the other one used RCP 4.5. So which means it works globally. But how about regionally? Then we focused on the impact at regional levels. This is just one example. I may stop here if the time goes. So I will just pick once. With this, we look at how could this affect drought management in Africa. Here, this is what we have comparing world with SAI with world without SAI. We see a decrease in potential evapotranspiration. That is logical because when you reduce temperature, the evaporative demand of the atmosphere will reduce as well. So that is good. But this is the impact on precipitation. We see that it suppresses precipitation over most part of Africa. Now, we then look at what does that mean to the major river basins that we have? This is just to summarize what it means. This is the world without geoengineering. This is the world with geoengineering. And we have two things there. SPI talks about, it's an indices to quantify drought. So this is the frequency of drought. If we don't account for the fact that atmosphere is also demanding for water, because drought has to do with water availability. So most of the time we think that, it's only rainfall. No, atmosphere also demands for water. So if we quantify that based on precipitation, that's what we have. But then if we account for the fact that atmosphere also demands for water from its surface, then the projected increase may be at that level. Now, this information is very good for basin manager. They look at this gap, and that tells them how much they should manage activities over their basin. They cannot reduce this. They cannot. So what will happen will be in between. There's nothing they can do about this, but they can limit the amount of water that the atmosphere gets from the surface using different strategies. So this is what we have, future without SARM. So that's what many people are preparing for now. But then, with SRM, what happens? This is what we have. What does it mean? There is no more gap for the manager to move around. Although the risk of this drought has reduced, but that one has also increased. Which means, as a water basin manager, there's nothing I can do. With this, I can plan. But with this, there's nothing I can do because the window is no longer there. Now, the take-home message here is this. We are busy preparing for impact of climate change, adaptation strategy, spending millions and billions of dollars to adapt. Implementing solar radiation modification can mess the whole thing up. That's the message there. We also look at the impact on water fluxes. I know you will say my time is up, so I will be fast. The main take-home message here, I will just focus on that. This is the present day. Future climate minus present day. Future climate, SAI minus present. this is how SAI could influence the future without SAI, in reference to world without SI. So let's focus on this. I will come to you later. So, this is evaporation minus precipitation. When it is negative, that is good. Because that means we have evaporation is less than precipitation. There will be fresh water available on the surface. But when it is positive, that's a problem. Because that means evaporation is more than precipitation. And if you look at what SAI could do here, we can pick that up, especially in Southern Africa, where we have the value positive, meaning that SAI could reduce the fresh water availability over the subcontinent. Well, people in West Africa will benefit from that, but it's not a good news for Southern Africa. So we also look at what it means to river discharge. It affects opposite results and so on. Then we look at the cloud brightness as well. With this, I will just go to the take-home message. The question is, if we are to inject aerosol over the ocean to do the SRM, where should we use? In this experiment, we look at 3 possibilities over this region. And the take-home message is that this seems to be the best region in terms of reducing the warming. For this, we have that. For that, we have that. This is the warming without. You see, you can't see much difference there. But this seems to be the best location. But how does it affect Africa? Because that's our concern. The one that seems to be the best, this is how it can change the temperature. It cools temperature there over West Africa, over most part of Africa, but then there may be some countries that may experience further warming because of that situation. Then this is for precipitation. See, drought in some places, especially with the one that we say is the best. You see the drought there, and so on. Then, lastly, we are currently looking at, okay, how can we what will be the impact of this for different strategy? The one we've just discussed is just to use it to limit to 1.5. What happens if we increase more aerosol to limit it to 1.0, or to reduce global warming to 1.0, or to 0.5? We supposed to release this in around 2035. We are working on it. If we don't do that, if we have a delay, how will that affect things? Now, remember I said that it does not address the root cause. And SAI is not sustainable. What does that mean? We cannot continue to inject aerosol into the atmosphere forever. So if we stop it, what will happen? That's termination shock. If we stop it here, the system will force itself back immediately. And that rate of warming may be too fast for a lot of activities. So we are busy analyzing that result, and we want to look at what does it mean to these different activities, grassland, our cattle, crop production, and so on. These are the teams that are working on that. And lastly, just to conclude, 1, SRM is not a silver bullet, because as it mitigates or reduces the impact of climate change in some area, it may actually aggravate it in other areas. So, as we also see that the impact is not uniformly distributed over Africa, it requires the stakeholders to come together to agree on whether we should use it or not. Because I won't want to suffer for it while other countries are really enjoying. Thank you very much.